Welcome back. In our previous video, we explored an example where the Picard iteration method didn't successfully find a solution, even though the equation satisfied Picard's conditions. If you haven't watched that video yet, we recommend checking it out first. It sets the foundation for today's lesson. In this video, we'll tackle this issue head-on by introducing a modification to Picard's method. This adjustment ensures that we can solve initial value problems, even in cases where the standard method falls short. Remember, each video in this series builds on the knowledge from the previous ones. So, if you're following along, take your time, review the earlier lessons, and practice. After all, practice is the key to mastering mathematics. Now, let's dive in and see how to adapt Picard's method to solve these challenging problems. Ready? Let's get started. Let's quickly recap why Picard's method didn't work for our example. The challenge arose during the third iteration, where we encountered an integral that couldn't be expressed in a closed form. This means we couldn't proceed with further iterations, leaving us without a solution. This limitation is why we need a modification to the method. Let's explore how we can overcome this obstacle and solve the problem effectively. The technique we're about to explore was developed by Edgar, Parker, and Sochacki. This method offers an innovative approach to solving initial value problems, addressing the limitations of standard methods like Picard's iteration. It's powerful, adaptable, and an exciting tool to add to your mathematical toolkit. This technique generates solutions as a Maclaurin series. Building upon the Picard iteration method, the Parker-Sochacki method is celebrated for its simplicity and efficiency. In this video, we'll demonstrate how this method successfully tackles problems that have challenged traditional techniques. So, grab your pencil and notebook, and get ready to be amazed. Let's dive in. We previously encountered an initial value problem that Picard's method couldn't solve. Now, let's solve this same problem using the Parker-Sochacki method, which offers a clever approach. As we go through the solution, we'll explain everything you need to know about this method, step by step, so you can apply it to solve initial value problems like this one. It seems the main problem we faced earlier was the non-algebraic sine function, which caused difficulties during the solving process. To address this, the Parker-Sochacki method introduces auxiliary variables, u and v. By defining these variables, we can overcome the issue. Next, we'll calculate their initial values at t equals 0, setting up the solution to proceed smoothly. Now, we need to find the derivatives of both u and v. Since y is a function of t, we'll apply the chain rule to calculate these derivatives. After finding the derivatives, we'll express them in terms of only u and v. If you look closely at the derivatives, you'll notice that on the right-hand side, we avoid non-algebraic functions like sine or cosine and have polynomials in terms of u and v. This ensures smooth integration during iteration, making the solution more manageable. These transformations help convert the original differential equation into a system of first-order polynomials. Now, we have a system of differential equations where the right-hand side consists solely of polynomials. This is crucial because it guarantees a smooth process during the iteration, making it much easier to solve, compared to dealing with non-algebraic functions. If you're enjoying this video so far, don't forget to like it, share it with others, and subscribe to the channel for more videos like this. If you have any questions or thoughts, drop them in the comments below. We'd love to hear from you. Next, we'll rewrite each equation into its integral form. The iteration process works in the integral form because it allows for successive approximations using integration. To begin, we'll write the Picard iterates. Now, let's provide the initial guesses for each variable, which will serve as the starting point for the iteration process. Next, we compute the first estimation using the initial guesses. This first approximation will serve as the basis for the next iteration, bringing us closer to the solution. Now, we move on to compute the second approximation. Using the first estimation, we refine our values to get closer to the true solution. Next, we compute the third approximation. By refining our values further, we continue to improve the accuracy of our solution. Let's first look at the first 5 approximations of the unknown function y. The exact solution to the problem is Finally, we'll provide the Maclaurin series for the exact solution. Now, we compare our approximated solution with the Maclaurin series and notice something interesting. The nth approximation matches the first n plus 1 terms of the Maclaurin series, showing that our method is progressively improving and getting closer to the exact solution. In practice, we can't always find a closed-form expression for the limit of the iterates. Instead, we settle for an approximation of the actual solution. However, obtaining a sufficiently accurate solution with a large n is practical because the algorithm is computationally efficient, making it a powerful tool for solving differential equations. In the next video, we'll answer a common question we often get asked. However, we encourage you to leave your comments or any questions in the comments below. We love hearing from you and look forward to your thoughts.